In the 30 years since Dr. Cam Lau invented the laser tracker, it has become the centerpiece of countless manufacturing environments across the globe. Trackers have evolved in that time to support tolerances that have grown tighter and production schedules that have become compressed. So much emphasis has been placed on the tracker accuracies and the capabilities of the probes and scanners that pair with them, and for good reason. But there is an often overlooked component of tracker operation and measurement: spherically mounted retroreflectors, or SMRs. SMRs play a vital role in laser tracker operation and performance. Their main function is to reflect the laser to the tracker with as little distortion or interference as possible. SMRs need to be lightweight, maneuverable, and accurate within a few microns across distances up to 80 meters. There are several factors that can affect SMR accuracy, including damage and temperature, and often tracker inaccuracies are traced back to SMR malfunction, which we will cover in another video. So for such a vital piece of metrology equipment, how do SMRs work? There are three main components to an SMR. The first is the outer shell or ball. It is most commonly made from stainless steel or aluminum, and while it might seem like a simple housing for the precision reflective properties inside, the sphere itself is where the high precision of SMRs begins. The alloy of the metal must balance magnetism and corrosiveness. The grade of the steel is also very important. Steel grades benchmark various dimensions and tolerances. The most common SMR grade is 25, which means they are guaranteed to be a perfect sphere within 25 millionths of an inch, with surface roughness and diameter tolerances also considered. The second component is the corner cube reflector. The corner cube reflector is how the SMR communicates with the tracker. The laser beam enters the reflector. It is directed to the center of the reflector for absolute precision and reflected back to the tracker in parallel, but slightly offset from the original beam. The offset is used by the position detector inside the tracker to better find the center of the SMR, which allows the tracker to adjust the laser and follow the SMR as it is used to measure. The third component is the reflective coating on the corner cube. Whether they are made from glass, steel, or aluminum, corner cube reflectors are then coated with silver or gold, and often a clear protective coat. Silver is more affordable, but is also prone to oxidization if scratched or damaged. Gold is more expensive, but more durable. It is important that the reflective coating affect the laser as little as possible. The position detector in the tracker uses the shape of the reflected laser to calculate the angle from the tracker to the SMR, making the z-axis position on the coordinate plane. If the shape of the beam is changed, the detector may record the wrong z-value or lose the SMR's position. In short, the three parts of the SMR, the sphere, corner cube reflector, and reflective coating, must all be designed, machined, and maintained to meet some of the tightest tolerances known to the manufacturing world. In the next videos, we discuss the various sizes and designs for SMRs, causes and signs of SMR inaccuracy, and the best practices for maintaining and extending SMR lifespans.